Hello my dear students, in this lecture we are going to see Amperes Circuital Law and we will see some few cases on Amperes Circuital Law. Now my dear students, let us understand regarding this Amperes Circuital Law. Now this Amperes Circuital Law is an alternate method to find magnetic field strength. Now here target is to find magnetic field strength, that is B. Magnetic field strength means B. This is a magnetic field, right? And the strength of magnetic field is calculated with the help of here this Amperes Circuital Law. But my dear students, it is an alternate way, like Gauss law. Now Gauss law is used to find the strength of electrical field, but this was the alternate way. And in electrical condition or for electric field, the basic law used was Coulomb's law. To find the strength of electric field, we have used Coulomb's law. And my dear students, here the basic law for calculation of magnetic field strength is Biot-Savart law. This T is silent, it is Biot-Savart law, right? But the special case, or we can say the alternate way for some special cases, is nothing but Amperes Circuital Law. Some special cases becomes very simple to solve with the help of Amperes Circuital Law, right? Now let us understand, but this Biot-Savart law is not for our syllabus here in this topic, in this electrodynamics. This is not for the syllabus. So my dear students, we will focus only on the Amperes Circuital Law, and whenever the result of Biot-Savart law is required, then I will tell you, don't worry about that. But for exam point of view, not required in this topic, right? Now let us say we have one charge I1, and let us say the charge is going inside perpendicular to this board, or for this screen, if I want to show one perpendicular charge going inside this screen, then the perpendicular charges going inside are shown with the help of cross mark. This cross mark means this I1 is going inside the board. And if I want, let us say one more charge is I2, and this dot mark means the charge is again perpendicular to the screen, but it is coming outside. It is coming outside from the screen, right? And I1 is going inside the screen, means angle between I1 and I2 is 180 degree, means from I1 I2 will get subtracted, right? This you have to understand. And let us say at point P, any point P, if I want to find what is the magnetic field, right? Here question will be find magnetic field strength at P, right? This will be the question. Now in this Amperes Circuital Law, we will understand first what procedure we have to follow, and then we will understand the statement of this Amperes Circuital Law, right? Now what we will do, let us form one loop around this I1 and I2. The loop must be symmetrical for I1 as well as I2. So here I will form one loop like this. Let us form one loop. Now my dear students, this loop is a circle, right? Here it is not a sphere, it is a circle, that you have to remember, right? Try to draw symmetric circle, right? This is my loop. Now my dear students, here for this loop I will assume some rotation. This is my just assumption. Let us say if I assume the clockwise rotation like this, if this loop is rotating like clockwise, if this is my assumption, therefore if I consider very small element at any location, let us say at this location, if I consider very small location, very small element dl, then the direction will be like this. This will be the vector dl, right? At any other location, let us say at this location, if I consider very small dl element, the direction will be like this, right? That is tangent to the loop. Likewise at each and every point you can understand, right? So here I have formed one loop, right? Now I have decided the direction of this loop, the rotation of this loop. Now I am assuming as the clockwise rotation. So my dear students, for clockwise rotation, now the which is positive, I1 or I2, this depends on the direction of loop. Now to decide positivity, we have to see for this loop, or if I assume this loop as an area, now for this area what will be the direction of area vector, that we have to understand. For this case we have right hand thumb rule. We have right hand thumb rule, or also called screw rule, Now see what you have to do, take a right hand. Now keep your thumb of the right hand perpendicular to other four fingers, right? And try to arrange your finger in such a case that, or try to arrange your thumb in such a case that the fingers will rotate along this loop. Means here around this loop you have to rotate your four fingers, and the direction of thumb will be the positive direction for I. Now for such clockwise rotation here, if it is a physical class I can explain properly, but let us understand with the help of screw rule I can explain it properly. See, for right hand thumb rule, what I am doing, I will take 4 fingers and 4 fingers of right hand, and I will try to curl or rotate these 4 fingers in the direction of rotation of loop. And the thumb direction, in this case thumb will be perpendicular to 4 fingers, and the direction of thumb will be the positive direction for current. In this case the thumb will be going inside. For clockwise rotation thumb is going inside. Or let us understand screw rule. Now you have water bottle as well as you have pen in your hand. Now try to open the pen and try to close the pen, means try to remove the refill from the pen. If I want to remove the refill from the pen, then I have to rotate it anti-clockwise direction. Means anti-clockwise direction means upward. Anti-clockwise direction means it is coming upward or outside. Right. Here I will write anti-clockwise means upward, or we can say outside. And if I rotate the pen, feel the refill, or to tighten the pen, I have to rotate clockwise. Clockwise means inward or inside. Inward or inside, right? Or inward or inside. Now it is clockwise rotation. Therefore for clockwise rotation I will be positive, I1 will be positive, I2 will be negative. Therefore net inside charge, I net, that is net inside charge, will be equal to, in this case, I1 minus I2. I1 will be positive. But don't worry, for our cases there will be only one charge inside. That's why always it will be simplest case. So don't worry about that, right? But this is for clockwise rotation. This is for clockwise rotation. If I assume anti-clockwise rotation, then I net will become, for anti-clockwise rotation, the outward direction will become positive, right? Therefore here this I2 will become positive, right? I net will be I2 minus I1. This is, my dear students, for anti-clockwise. This you have to understand, right? So my dear students, here with the help of right hand thumb rule or screw rule, we have decided that positive and negative I's, right? Now my dear students, here Amperes Circuital Law says that, see, line integral of magnetic field, here for a closed loop, line integral of magnetic field for a closed loop, this is a line integral, right, is equal to mu naught I inside. Mu naught I inside. Now let us understand what they are trying to tell you, right? Now my dear students, here it is a line integral for this Amperes loop. This loop is called Amperes loop, right? This loop is called Amperes loop. Therefore line integration around this Amperes loop, B dot dl is equal to mu naught I inside. I inside we understood, mu naught is nothing but permeability of free space. This mu naught is, I think you know this basic terminology, permeability of free space, right? This will be the mu naught, which is also called permeability of free space. So let us understand this Amperes Circuital Law in terms of wording. Here the law I will write in terms of wording. Here this Amperes loop, you understood. Amperes loop is nothing but, if I want to find magnetic field, strength of magnetic field at any point P, with the help of this point P, I will form one symmetric loop around this current, right? Current inside, right? And from this I will get, with the help of Amperes Circuital Law, I will get the strength of magnetic field. Now my dear students, let us understand here with statement. Here the Amperes Circuital Law is a line integral, it is a line integral, right, of a B field or magnetic field, B field or magnetic field, right? Line integral of a magnetic field, see, B dot dl means it is a line integral, right, of a magnetic field for a closed loop. This is important, it is a closed loop symbol, right? In a closed loop, is equal to, see, whatever we have written here is nothing but this line integral or integral over a closed loop B dot dl, right, is equal to mu naught times, right, the net current flowing inside, net current flowing inside the loop, this is important, right? So my dear students, it is a line integral, means around this line we have to take the integral, right? This is called Amperes Circuital Law. Now let us understand when this law is useful, right? The conditions to apply this Amperes Circuital Law, sometimes they will ask in the exam also. So my dear students, this is the Amperes Circuital Law, that is line integral over a closed loop of a magnetic field is equal to mu naught I inside. Now my dear students, this law is useful if, means conditions, whenever we can apply this law, these conditions we are going to check. See, this law can be applicable anywhere. In Gauss law also I have stated you that the Gauss law is applicable anywhere, but the Gauss law is not useful everywhere, right? But we can apply. Similarly, this Amperes Circuital Law we can apply anywhere, but for complex conditions the calculation becomes so difficult that in graduate level we cannot solve such cases, very complex cases. That's why there are some special cases where this Amperes Circuital Law becomes very simple. So in that case only we are applying this law, means these are the conditions to apply the law. Now there are 4 conditions. Understand, first condition means is the magnetic field is tangential to the magnetic field is tangential to length, and magnetic field is non-zero and constant, and magnetic field and B is non-zero and constant. That means my dear students, here this law, which is the law here, cyclic integral of B dot dl will be equal to mu naught I inside, right? Therefore here this magnetic field is tangential to the length, means they are tangential, means angle between them is 0 degree. That means both are tangential, means both are going in same direction. This is the magnetic field and this is the length dl, right? Angle between them is 0 degree. Therefore the dot product becomes cyclic integral of B dl cos theta, right, is equal to mu naught I inside, right? So my dear students, again what will become? The magnetic field is constant, cos 0 is 1, and integration of dl becomes, it is nothing but total length of this loop. Therefore it will become BL is equal to mu naught I. This is how we can solve, because cos 0 is 1, right, and B is constant. Here they are saying B is constant. This is how the law will convert in very simple form. And today whatever the numericals we are going to see is on this condition only, means in all the numericals the length and magnetic field will be tangential to each other, means theta will be always 0. This remember, right? Second very special condition is if B is normal to the length at each and every location. B is normal to length. Normal means perpendicular to length, means perpendicular to the dl, means let us say this is the dl direction and this will be the B direction. So my dear students, angle between them is 90 degree. Therefore cos theta, which is nothing but cos 90, will become 0. So my dear students, here always this cyclic integral of B dot dl, which is nothing but mu naught I, will also become equal to 0, because this will convert to the B dl cos theta, and cos theta is 0. Therefore this is always equal to 0, right? This is how we can apply very simply, or for normal to the length. Magnetic field is normal to the length. Third, we can apply this law whenever B vanishes. B vanishes means the net magnetic field there is 0. The net magnetic field is 0. So definitely we can apply this law, right? Here directly we know the value of magnetic field, which is 0. And last is, this law is very much useful for higher symmetry. Very much useful, we can say, for higher symmetry. Whenever the charge is very symmetric about the loop, then this law is very best. Instead of Biot-Savart law, we will go for Amperes Circuital Law for quick results whenever there is a higher symmetry with respect to charge, right? Now let us say, my dear students, there is a I1 going inside, cross means going inside, I2 coming outside, right? And at point P, I want to find the magnetic field or the strength of magnetic field. Now what I will do, I will form a loop with respect to point P, passing through the point P around this I1 and I2. I will form one loop passing through P, and which will be having I1 and I2 will be enclosed or inside the loop, right? Now my dear students, let us say there is one more charge, or there is a current carrying wire I3. It is going inside the board, right? Cross means going inside the board, and one more current I4, which is coming outside the board. Dot means coming outside the board at this location, right? Now I3 and I4 are outside. Definitely I3 and I4 are outside. Now while applying the Amperes circuital law, that is cyclic integral of B dot dl is equal to mu naught I inside. Now here, first of all, we have to decide the direction of loop. Let us say if I decide direction of loop as clockwise, then I1 will become positive, I2 will become negative, and the I inside for clockwise rotation will be I1 minus I2. Means here only inside charges we have to consider, or only inside current carrying wires we have to consider. Inside currents we have to consider simply, right? Don't say charge, because whenever there instead of charge, it is a right word to say current, right? Inside currents we have to consider, right? So my dear students, but in this law, this magnetic field, see here in right side it is I inside only, but this magnetic field is because of all the four currents, right? This magnetic field is due to all I1 also, I2 also, I3 also, and I4 also. Means all inside as well as outside we have to consider while calculating magnetic field, but the result will be only inside will be remaining, right? This is very interesting result, right? Now with the help of this Amperes circuital law, remember the line integral of magnetic field for a closed loop, right? It is a line integral of a magnetic field for a closed loop is equal to permeability mu naught into I inside. With the help of this Amperes circuital law, let us solve few cases. Now let us solve the first case, that is magnetic field due to infinite straight current carrying wire. Let us say I have one current carrying wire. Let us say the current carrying wire is like this. This is my current carrying wire, and through this wire current is flowing. And let us say my assumption is current is going in upward direction. You can assume downward also, no problem. Now here current is going in upward direction, and I have to calculate the magnetic field at any point P. Let us say this is a point P. At this particular point P, at a distance r away from the wire, I have to find the magnetic field. Now what I have to do? With the help of this point P, I have to form one loop, right? So let us form one loop like this. The loop will become like this. This should be the loop, right? Now my dear students, and the current is flowing like this. Current is perpendicular to the loop, right? Now here for this point P, now if I see top view, let us understand. See my dear students, with the help of Biot-Savart law, the result was this B is equal to mu naught I divided by 2 pi r. This is a result with the help of Biot-Savart law. But as Biot-Savart law is not for the syllabus, don't worry. With the help of Amperes circuital law also we will prove the same result, right? Now if I check the top view, let us see from the top. I will check the top view, right? In top view, this wire I will see as a point, and current is going outside from the loop, means dot. There will be a dot, and this loop will be circular, right? Therefore in top view I will see the loop like this. The circular loop I will see. This is how the loop will form, right? And my dear students, the wire will be here, the point. And why it is point? Because the current is going upward. Outward means point. Inward means if it is downward. Inward means here cross, right? You can understand, very simple. And as here the current I, net current, total current is I only inside. As it is going outward, therefore for anti-clockwise rotation it is going outward. Therefore the direction of loop I have to assume as anti-clockwise. This should be the direction of loop, right? Now my dear students, on this loop, if I consider very small elemental ring, let us say very small length dl. Now this tangential will be the direction of dl, as well as the magnetic field direction is also same in the direction of rotation of loop. This is a magnetic field direction. In the direction of rotation of loop, this is a magnetic field direction. Magnetic field lines are in closed loop na. Already we have seen in previous lectures, right? Let us form here. If I consider the small dl length here, therefore the rotation is, you can see the rotation will be like this, tangential, and in the same direction there will be a B, magnetic field vector, right? Means here always all cases will be theta is equal to 0. For all cases here, for our syllabus is theta is 0. Don't worry about that. So here my assumption is they are tangential. So first condition is satisfied, they are tangential. And here see the distance, radius r at each and every location is same. I can consider the element at any location. At any location radius is r only for this loop. Means the distance is same. Therefore as the distance is same, this magnetic field will be same. Means it is a case of constant magnetic field and theta is equal to 0. And always it will be the case. Constant magnetic field and theta will be 0. Right. So don't worry about that. Now let us apply the here Amperes Circuital Law. What is the Amperes Circuital Law? Amperes Circuital Law says that the line integral of magnetic field for a closed loop, that is Amperes loop. This is the Amperes loop. For Amperes loop we have to apply line integral, right? Is equal to mu naught I inside, and I inside is I here, right? So my dear students, here magnetic field is constant, therefore this line integral becomes B dl cos theta cos 0, right? Here this cos theta, this step I am not going to write always. This directly, this step I am going to write as BL. From here onward I am going to write BL. This complete term, integration term, is equal to mu naught I. See again what becomes, B is constant. Integration of dl cos 0 is 1 is equal to mu naught I. Therefore the term becomes, see term becomes B integration of dl is equal to mu naught I, and the dl is nothing but on this loop. Therefore all lengths are added, we will get perimeter of this loop of radius r. Therefore the total length integration of L will be BL is equal to mu naught I. So here onward direct with this step, for further cases direct with this step I will start, right? BL is equal to mu naught I. Therefore what will be the length? 2 pi r. Here perimeter, that is circumference, B into 2 pi r is equal to mu naught I. Therefore B will be equal to mu naught I divided by 2 pi r. See, with the help of Biot-Savart law and with the help of Amperes Circuital Law you will find same result. Now here we will draw a graph of magnetic field versus r. Here can I say the magnetic field, the strength of magnetic field is inversely proportional to radius or the distance of this point from the here wire. Therefore as I go away the strength of magnetic field is decreasing, and near to the current carrying wire the strength of magnetic field is very high. So let us understand the graph. Let us understand the graph. If I draw here graph, see on y-axis I will consider magnetic field. On y-axis I will consider magnetic field strength, and on x-axis I will consider the distance of point from the wire. Now whenever the r is 0, magnetic field is infinite. Whenever r is 0, magnetic field is infinite, and as r is increasing the magnetic field is decreasing because it is directly inversely proportional to r, right? It is coming from the infinity. On the wire it is infinite, right? This will be the graph. I hope you understood. This is for the current carrying wire. Now let us understand the second case. That is find magnetic field. Here we have to find strength of magnetic field, that is B field, right? I will highlight this magnetic field due to infinitely long cylindrical wire. Now wire is infinitely long cylindrical, current carrying wire on its surface. Now carrying current on its surface, this is very important. Now wire is carrying, here cylindrical wire is carrying current only on the surface. Inside the cylinder there is no current. Current is only on the surface. Therefore it is a case of hollow cylinder, right? For hollow cylinder only the current is on the surface, inside there is no current. For solid cylinder the current will be inside also, definitely, right? So my dear students, see if I check here, it is a cylindrical wire. See, therefore if I check like this, it will be cylindrical, right? And here these both sides of the cylinder are extended to the infinity. Therefore here you can check both sides I am extending to the infinity. it is very long. Long means infinite length, right? And the charge or the current, sorry, the current is only on the surface. Inside there is no current. Therefore, my dear students, the current, let us say I am assuming the current is flowing vertically upward through this cylinder. This is the direction of current, and total current through this surface of cylinder is nothing but I, right? And here let us say this cylindrical surface will be having some axis. Let us say this is the axis of cylindrical surface. Here this is the axis of cylindrical surface. Now my dear students, at any point, let us say the radius of cylindrical surface is r. Here from the axis the distance of surface is r, that is radius of cylinder is r. This is my assumption, and length is infinite. Capital R is the radius, right? Now they will mention everything in the question if they form question on this, right? All the possible cases we are looking here on this question or on this special case. Now let us say the point can be from this axis, can be inside this cylinder or can be outside the cylinder also. Now let us consider the inside point. Let us say point P. If I consider point P, which is inside at distance r. First case, I am assuming the point P inside point to the surface, right? Now what we have to do here, we have to form one loop with point P. Therefore let us form one loop with the help of this point P. We are forming one loop, right? And my dear students, let us check this loop. If I see top view, in top view you will get clear idea. Now see here in top view the current is only on the surface, means at this point, at this point, at this point on this surface. Inside there is no current, and dot means outside. Dot means it is upward, current is going in upward direction. This is dot I have shown. Now from top if I check, I will get one loop for inside point. First case for inside point. Inside point means the small r is less than capital R. Small r less than capital R. This condition we are looking. See, if I check this cylinder from the top, this cylinder will look like this, and the charge is or the current is only on the surface of cylinder and going outside, right? Going outside or upward means a dot like this I can show on entire circumference, on entire circumference, and the total current is I to this complete length. The total current is I, right? And my dear students, this distance is capital R, and we have considered one point P inside, right? And if I form here loop at distance r, see the loop will be circle like this. But what is the law here? BL, see special case only, that is integration B dot DL tends to BL, where EL is a length of loop, where EL is a length of this Amperes circuital loop. Here this is a wire, this is a wire, and Amperes loop is this. This is a Amperes loop, right? And EL will be length of Amperes loop. So the special case becomes BL is equal to mu naught I, right? Therefore here I can write BL is equal to mu naught I inside, right? Here length I know, for this loop length is nothing but B into 2 pi r, small r, because Amperes circuital loop we have to length consider for Amperes circuital loop, right? But I inside is 0. There is no inside charge for this loop, therefore is equal to 0. Therefore my dear students, this B will be, the strength of magnetic field will be 0. Means for this cylinder, hollow cylinder, the charge is on the surface. Inside this cylinder there is no magnetic field. Inside surface there is no magnetic field. Now let us understand, if I consider point outside. Now let us understand, inside we understood. If I consider any point outside, so I will erase this. Inside we understood, always it is 0. Now let us understand the point outside, right? Now my dear students, let us say point Q is outside the loop. Here I will say the point Q is somewhere here. Let us say this distance is r. R is variable, na? The small r is variable. It can be inside also, it can be outside also, it can be on the surface also. Now my dear students, for this outside r, form the loop again. Now if I form the loop, now outside is a red color loop, this loop, right? Now if I see from the top, this loop is outside this complete charge or complete current. Therefore here the loop, Amperes loop will be outside like this. See, this will be the Amperes loop. Try to draw proper circle. This will be the distance r, and here the wire radius is smaller, the capital R, sorry, right? Means here it is a point outside, the point outside. Here we can say the second case, which is nothing but second case for outside point, that is small r is greater than capital R. Now my dear students, again the Amperes circuital law is BL is equal to mu naught I inside, right? I inside. Now again the L is nothing but length of Amperes loop, and here red color is Amperes loop. This is a Amperes loop, which is red color, right? Therefore B is constant, therefore B into length of Amperes loop will be 2 pi r for red color. Circumference is equal to mu naught. Now I inside is total current I inside is total current I, therefore is equal to into I. Therefore my dear students, this B will get mu naught I divided by 2 pi r. See, it is the result is exactly same like current carrying wire. Now this loop don't know whether inside the current is flowing through the surface or through the only one wire, right? This loop don't know. This loop will count total current inside, therefore total current inside is counted, right? So again for outside point we can say B is inversely proportional to radius, but for inside point B was 0. So let us understand diagrammatically. So my dear students, here we have this cylinder, and through the surface of wire the current is flowing, right? And here we have axis of cylinder. Let us say this axis of cylinder as y-axis. This is our y-axis, and on y-axis we are considering plotting magnetic field, right? And on x-axis we will plot R, right? Now we have seen for inside, if the loop is inside, B will be 0. Already we have seen whenever inside. Therefore up to R, up to capital R, means this is the inside, this much distance, the magnetic field will be 0 only. And at this location suddenly magnetic field becomes maximum. At this location magnetic field becomes maximum. Therefore here there will be a sudden increase like this, means from 0 0 0 and then suddenly maximum, right? And from this location maximum is mu naught I divided by 2 pi r, capital R. Here there will be a capital R, and from there onward as R increases it is inversely proportional to R. Therefore the graph will go like this. Here B is inversely proportional to R. This is a curve. Inversely proportional means this curve, there will be a curve like this, right? I hope you are understanding, right? Let us understand the third case. Let us say what happens if this is a solid cylinder, means it is complete solid cylinder, means current is flowing through inside also. At each and every location current is flowing, means it is a bundle of small wires. It is a bundle of small wires, right, packed in cylinder. Let us understand this case, third case. Now let us move for the third case, that is magnetic field due to infinitely long cylindrical wire carrying current if current I is distributed uniformly across its cross section. Now current is distributed uniformly across its cross section. Now let us say if I consider infinitely long cylindrical wire like this, means it is a wire only but the diameter is more, diameter of wire is more, simple case, right? Now therefore it will become cylinder. The wire, same wire will become cylinder if it is having more diameter, right? Let us say this is the wire. If diameter is very small it will become only length, right? But if it is like cylinder and it is infinite in length, on both sides it is moving towards infinity. And my dear students, means you can say a bundle of wire, small wire is coming through this, right? Now means current is at each and every point. Let us say, assume that current is flowing in upward direction. Total current I is flowing in upward direction. Now through which point? On the surface if I check, it is flowing through the complete surface also and inside also. This dot means upward. See, inside also there is a wire, small wires, and through all these wires the current is flowing in upward direction. These dots I have shown small wires. It is a bundle of wire, group of wires together bounded in a cylinder, and current is flowing through each wire in upward direction, that means dot, right? And for this case we have to find, let us say axis from axis at any distance r, we have to find the strength of magnetic field. Let us say this is the axis of cylinder, Wait, let us say this is the axis of cylinder. From this axis, the radius of cylinder will be r. Here the radius of cylinder will be r, capital R. Capital R is the radius of cylinder, and any point we have to consider. Let us consider, if I consider a point inside, let us say point P is inside. This is a point P inside, right? Now my dear students, here from this axis, let us say the point P is at distance small r. Now what is the procedure? We are forming one loop at this point P. We are forming one loop like this, and through this loop also, my dear students, the current is flowing. See, current is flowing through this loop also. You can see the current here, small wires like this. All these wires are carrying current. All these small wires are carrying current, and current is flowing in upward direction through each and every wire, right? And total current is I through this complete cylinder, right? Means through this very small loop also, this Amperes loop also, the current is flowing, right? So my dear students, here if I check top view, first case is for point inside cylinder, means small r is less than capital R. Now if I check top view, from the top view, see, for top view we have to see from the top, right? From top, if I see, I will get top view. Now the wire will look like this. Let us say the wire will look like this, right? Circular from the top view, and it is the center, right? And here through every point there will be dot, means through every point in the cylinder, through there are n number of small wires in the cylinder, and through every wire the current is coming outside. Dot means coming outside through the surface also, and here radius of wire is r. This is our wire, total wire, right? And the point P is inside the wire. Now if I form a loop, see, loop is circular only like this. Now what will be the length of loop at radius r? The loop will be at radius small r. Therefore the length of the loop will be, my dear students, here length of the loop will be 2 pi r, right? Definitely. Now let us apply the Amperes Circuital Law. Now my dear students, inside current we have to consider, and there is some current inside also. Total current is I, but there is some inside current also. Therefore there will be a concept of current density. There will be a concept of current density. J is nothing but current density. It is nothing but current carrying through the wire per unit area. J is nothing but current carrying through the wire per unit area. A is area, and which is always constant here. For this case they have mentioned it is a uniform. See, current I is distributed uniformly across the cross section. Across the cross section it is distributed uniformly. Therefore current per unit area is constant. Uniform means constant. Therefore my dear students, here can I say area is nothing but pi r square for the loop, Amperes loop. This is the Amperes loop, and for this wire area will be pi capital R square, right? So this current density will be equal to I, total current divided by total area, is equal to I inside divided by loop area. Therefore this I inside I will get small r square divided by capital R square into total I, right? This will be the inside current. So I have calculated inside current. Now the rest calculation is very simple. Now we know that Amperes Circuital Law, here line integral over a closed loop B dot dl is equal to mu naught I inside, and this B dot dl, line integral of B dot dl becomes BL. Special case means here B and dl are tangential and angle between them is 0 degree. This is a special case, right, at each and every point. Now so my dear students, here the law becomes BL. No need to explain again and again. Many times we have explained the same. BL is equal to mu naught I inside. Therefore L will be 2 pi r for the loop. L is for loop. Therefore my dear students, here B will become mu naught I inside is r square I divided by capital R square divided by L is 2 pi r. So one r will get cancelled, small r, right? So my dear students, what will be the B? I will write here at the top. Let us say I will delete some case here. I will delete the question. case I will delete. No worry, you have already written the case, right? Now let us understand for the B. Therefore, my dear students, this B will become equal to here mu naught I R divided by 2 pi capital R square. Therefore, for inside condition, when your point is inside, this B is directly proportional to R, but it is for inside condition, right? Now let us simultaneously draw the graph, right? So just a minute, for graph I have to delete everything inside, right? See, I am deleting these conditions, right? And along the axis I will consider magnetic field in y direction. Let us say the magnetic field is considered in y direction. In this direction magnetic field we are considering, right? For the graph, my dear students, for the graph, and in this direction we are considering R, right? In this direction we are considering R. Now for inside, B is directly proportional to R. Therefore inside there will be a straight inclined line, directly proportionality, and it will become maximum on the surface. That is, B is directly proportional to R, right? Here from the derivation we have seen. Now let us consider a point outside. For a point outside we will consider. So let us consider outside point outside, that is R greater than R, right? So second condition I am considering. Here I will delete everything, and let us solve for the outside point. Outside point is very simple. For outside point it is very simple, right? Because it is just a current carrying wire for complete loop, right? Therefore see, second outside point, that is small r is greater than capital R. Therefore I have to consider any point. Let us say point is considered Q somewhere here at distance R from the axis. Now from the Amperes loop, this will be your Amperes loop, right? And if you check here, the wire will be like this, and through this wire at each and every point current is flowing uniformly outward. Outward means dot, inward means cross, already we have seen. And the Amperes loop is outside this wire, right? Now this is Amperes loop, Ampere loop, and here it is a wire. Wire radius is capital R, Amperes loop radius is small r, right? Now say, what is the law? BL is equal to mu naught I inside. Now here I inside is total I, because total wire is inside. For this loop the wire is simply, it is a wire, it is not a cylinder. For loop it is a wire, like the wire case only, first case of wire. Therefore B will become equal to mu naught into I divided by L. L is the length of loop, it is 2 pi R, right? Simple case. Therefore B is inversely proportional to radius, or R, distance from the wire, distance from the center of wire or axis of the wire, right? So my dear students, for outside, see, on the surface, on this surface, when your small r becomes equal to capital R, this is the inside, directly proportionality. Now outside, after going outside, there will be inversely proportionality. Therefore afterwards there will be decrease in the magnetic field, right? Strength of magnetic field as radius increases. This is for outside, inversely proportional to R, right? So this will be the graph. This will be the graph. I hope you are understanding, right? Now let us consider one more case, very special case, little bit tricky. In this case we have assumed that here the current density J, which is nothing but current per unit area, is uniform, constant. This is our assumption in this case. But what if this current density also changes? This J is variable with respect to R. Then what happens? Let us understand this case. Now let us understand the fourth case, that is magnetic field at distance R from the axis of long straight cylindrical wire carrying current I, total current is I, such that current density J is equal to J naught R. Here J naught is constant and J is function of R. J naught is constant and J is a function of R, right? So here can I say J naught is constant, here J naught is constant and J is directly proportional to R. Means here current density is variable, here current density is not constant. So my dear students, previous case we cannot use. Here current density we are changing. Let us say we have one cylinder, let us say infinite cylinder like this, through which current is flowing. Total current is I. So for outside point we are not going to calculate, because for outside point it is exactly similar to all previous three cases. For outside point, if it is outside point, the B is going to be mu I, already we have seen, divided by 2 pi r, right? Always for outside point, right? So this we are not going to calculate. Let us check for inside point, right? Let us say this is an infinitely long cylindrical wire, and here current is flowing through this complete wire, but the here current density is variable. Let us say this is the axis of wire, this is the axis of wire, right? Now radius of wire I am assuming as capital R, and let us consider one point inside, because for outside point it is always same like previous cases. Let us say this is a point P at radius R, right, from the axis. Now we have to form a loop like this. The procedure is similar. Now I have formed the loop. Now let us check. If I check the top view, see current is flowing through this complete wire. Dot 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 means at it is a group of wire, bundle of wire, right? And current is coming out from this bundle of group of wire like this. The current is coming outside like this, right? You can assume upward direction like this. Total I is current, right? Now if I check top view, what I will check, right? Top view, see this will be the wire. Carefully observe, my dear students, it is a very special case, right? Let us say this is a wire, this is the axis, right? And current is uniformly distributed. Here current is completely flowing through this complete wire. Dot 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 means it is coming outside. All dot means it is coming outside. I hope these simple points you are now able to understand, right? And this is my wire. This is my wire. Now let us form one Amperes loop at point P, right? This will be our Amperes loop, right? This is our Amperes loop at point P, and this point P is at radius R, and wire radius is capital R. Wire radius is capital R. I hope you are understanding, right? Now through this loop also current is flowing, but with variable current density, right? Current density is variable, not constant. So my dear students, what will be the case? The Amperes circuital law says that BL is equal to mu naught I inside, where therefore B into L is length of loop. Don't worry about the length of loop. L is 2 pi r, small r. Don't worry about the length of loop, right? Only target is that this I inside we have to calculate, right? We have to calculate the I inside this loop. So my dear students, what I will do, I will consider this loop because current density is changing at each and every location. If R is 0, see, if R is 0, current density is 0. If R becomes 1, current density becomes J naught. If R becomes 2, this current density will become 2 J naught. Similarly, it is going on increasing, and on this loop the current density will be maximum for this loop, right? So current density at each and every point is different. So previous case we cannot use here. So to calculate I inside, we have to consider this loop, and inside this loop we have to consider very small elemental ring, right? And for this link, very small I we have to calculate, and we have to integrate over entire length, right? This is the integration method. So let us understand whatever I have told you here. Let us solve this. Now here I will consider only Amperes loop. See, this red color is a Amperes loop na. So I have considered here only Amperes loop of length L. This is my Ampere loop of length L, 2 pi r, that is 2 pi r, right? Now let us consider very small elemental ring inside this loop, right? If I consider very small elemental ring inside this loop of at distance x of thickness dx, right? This elemental ring is of thickness of distance x at distance x of thickness dx. The thickness of ring is dx, right? Very small ring I have considered. So we know that already, and the here loop radius is small r, right? We know that the current density is nothing but J naught r. R is nothing but x here, and R is nothing but x. So I can write it is equal to J naught x. Likewise also I can write, right? And x varies from 0 to small r. Inside loop we have to calculate inside loop 0 to small r, not capital R, because we are calculating inside, right? Inside loop we are finding current. Then R will change from 0 to capital R. Don't worry about that. X is changing from 0 to R, but R is changing from 0 to capital R. Don't worry about that, right? So my dear students, here this J is nothing but for this very small elemental ring. If I open this ring, this will look like this. make this ring straight. It will become a length of 2 pi x. 2 pi x, we have considered x here, and thickness dx. Therefore, for this ring, very small area will be dA, which is the number 2 pi x dx. See, it is very simple. Length into height, this will be the area, 2 pi x dx. And through this very small area, now the current is very small, di, which will be equal to current density into dA, right? Therefore, this di very small will be equal to current density is jx into here area is 2 pi x dx. Now, if I want to calculate total current flowing through this loop, I have to integrate from 0 to small r. Therefore, if I integrate both sides, that is x changes from 0 to small r, then I will get total current flowing inside, which will be equal to, it is j naught, right? It is j naught x. J naught is constant, 2 pi is constant. Therefore, it will become j naught into 2 pi outside integration 0 to r, limit is x square dx, right? X into x, x into x, it will become x square, right? X into x, right? Therefore, what is the integration of x square? It will become 2 pi j naught. Integration of x square will be x cubed divided by 3, but x changes from 0 to r. Let us put the limits. Therefore, this current becomes 2 pi j naught into r cubed divided by 3, right? This should be the current. Now this r changes from 0 to capital R, means maximum current will be on the surface, minimum current will be on the center. Likewise, the current is slowly increasing, right? Now this is I inside. Now let us use the formula. Now it is very simple, direct formula we have to use. Now what was the formula? That is Amperes Circuital Law. From the Amperes Circuital Law, we know that BL is equal to mu naught I inside. Therefore, B is nothing, B is equal to mu naught I inside is 2 pi j naught into r cube divided by 3 divided by length. Length for the loop is 2 pi r. So 2 pi will get cancelled, 1 r will get cancelled, right? Therefore, this B will become equal to mu naught into 2 j naught r square by 3, right? I hope you are understanding this, right? 2 pi j naught r square by 3. So for inside, B is directly proportional to r square. This is for inside, my dear students, for inside, right? But for outside, always we have seen, for outside, if I consider any loop, the B will become always mu I naught divided by 2 pi r. It is for outside. If the point is outside the cylinder, the B will be inversely proportional to r, but this is for outside. If the point is outside the cylinder, and if it is inside the cylinder, the formula is written here, right? So if I want to draw the graph, what will be the graph? Now, my dear students, on y-axis I will draw magnetic field density, on this axis r. Now inside is this line, that is r is equal to r. I mean, this is the inside, this portion is inside the inside the cylinder, right? This portion is inside the cylinder, and above this portion there is outside the cylinder, right? Now inside, it is directly proportional to r square, means it is an increasing curve with faster rate. Therefore, from 0, see, whenever r is equal to 0, the B will be 0, and whenever r becomes capital R, B becomes maximum. Therefore, it is increasing with faster rate. Inside, it is B is directly proportional to r square, and outside it is decreasing smaller rate or slower rate, inversely proportional to r. Outside, B is inversely proportional to r. So one thing we understood, that on the surface, the magnetic field strength is maximum. So from all cases, we understood that on surface of wire, any wire, whether it is a hollow cylinder or solid cylinder with variable the current density, or with solid cylinder with constant current density, or it is simply a wire like one line, then on surface of wire, B field is maximum. The magnetic field strength is maximum. This point you have to understand. I hope you understood everything. This is all regarding Amperes Circuital Law. Thank you, dear students. In next lecture, we will see Maxwell's equation.